Somewhere in your pocket, your bag, or the wall beside you, there is a piece of metal so light it can float on oil. It powers your phone, your laptop, the flashlight app you used last night, and if you drive an electric car, it moves you down the highway at 70 miles an hour. That metal is lithium, and for the last 2 decades, almost none of it decided where it came from without a handful of countries controlling the tap. Picture every lithium-ion battery on Earth right now, in phones, laptops, power tools, home batteries, and electric cars, laid end to end. That chain would wrap around the planet several times over, and it is growing by the hour. Every one of those batteries starts the same way. As a mineral, dug out of a salt flat or a mountain, thousands of miles from the factory that turns it into power. And for most of modern history, 3 places controlled almost all of it. But here's the part most people never hear about. More than half the world's known lithium has sat in just 2 regions: the lithium triangle of Chile, Argentina, and Bolivia in South America, and a stretch of salt flats in the western United States. Everyone else, including the world's largest buyer of lithium, has had to import it. That buyer is China, and in 2024 alone, it imported well over half the lithium it needed to keep its battery factories running. Being the world's biggest battery manufacturer while depending on someone else for the raw material is like owning the world's busiest bakery and not being sure you'll get flour next month. That is the quiet risk that has been sitting underneath the entire electric vehicle boom. In January of 2025, the China Geological Survey, an institution under the Ministry of Natural Resources, announced the result of a nationwide search that had been running since 2021. It was not one discovery, but a chain of them, and together they moved China from 6th place to 2nd place in global lithium reserves almost overnight. If you enjoy videos about resource discoveries and engineering breakthroughs that quietly reshape global industries, hit like and subscribe so you never miss one. So why did it take until 2025 for China to find lithium it had apparently been sitting on for years? The honest answer is that easy lithium was never evenly spread across the planet. The lithium triangle in South America and the salt flats of the western United States happen to sit on unusually pure, unusually accessible brine deposits, formed over millions of years in closed desert basins where water evaporates faster than it arrives, concentrating lithium salts near the surface. China's geology is different. Its lithium is scattered across harder rock, deeper brines, and mineral forms that were, until recently, expensive or outright impractical to process. One of the biggest culprits was a mineral called lepidolite, a lithium-bearing mica found in provinces like Jiangxi and Hunan. Lepidolite looks promising on paper. It contains real lithium. But extracting that lithium cleanly, without enormous energy costs and mountains of waste, was for decades considered barely worth the effort compared to just buying refined lithium from South America or Australia. So mining companies did the rational thing. They imported. It was not laziness, and it was not a failure of ambition. It was basic economics. The same reason you don't mine gold out of seawater even though technically it's there. The gap wasn't a lack of lithium, it was a lack of a cheap, clean way to get it out of the rock China actually had. That gap is what closed between 2021 and 2025, and it closed on 2 fronts at once: better extraction chemistry, and simply looking in more places, harder. The transition point, the moment the story changes from expensive rock to world-class resource, happened underground on the Qinghai-Tibet Plateau. For years, geologists suspected the plateau held more lithium than anyone had confirmed. It's one of the most geologically active, least accessible regions on the planet, sitting at elevations above 4,000 meters, where surveying equipment and personnel operate in genuinely brutal conditions. Between 2021 and 2025, teams working under the China Geological Survey systematically mapped salt lake basins across the plateau, alongside a newly identified spodumene belt in the west of the country, spanning roughly 2,800 kilometers through the West Kunlun-Songpan-Ganzi region. Spodumene is a hard rock lithium mineral, and this single belt alone was confirmed to hold more than 6.5 million tons of proven lithium, with the China Geological Survey estimating a resource potential of over 30 million tons once fully explored. But the number that actually rewrote China's position in the global supply chain came from the salt lakes. Combined, the newly mapped Tibetan Plateau salt lake deposits were confirmed to hold more than 14 million tons of lithium. According to the China Geological Survey, that figure made China's salt lake reserves the 3rd largest in the world, trailing only the lithium triangle of South America and the brine deposits of the western United States. Senior CGS scientist Wang Denghong, who has led lithium exploration efforts at the institution since the program began in 2021, described a broader pattern of discovery across the country. Roughly 10 million tons of lepidolite lithium ore confirmed across Hunan, Jiangxi, and Inner Mongolia, another 10 million tons of brine lithium in Qinghai, and 10 million tons of spodumene lithium in Xinjiang. Salt lake extraction matters here because it is genuinely different from hard rock mining. Instead of blasting and crushing rock, brine is pumped from underground, spread across enormous evaporation ponds, and concentrated naturally by sun and wind over months until lithium salts can be separated out chemically. It's lower cost per ton and produces a fraction of the waste rock that hard rock mining leaves behind, which is part of why the lithium triangle became so dominant in the first place. Geography did the concentrating for free. China's plateau salt lakes work on the same principle, just at extreme altitude and in a harsher climate, which is exactly why they took longer to map and develop. Think of it this way. Hard rock mining is like cracking open a safe to get at what's inside. Salt lake brine extraction is more like letting the desert itself do the safe cracking, one evaporation cycle at a time, while you simply wait and collect. The trade-off is time. A single evaporation cycle on a salt flat can take months, sometimes close to a year, depending on climate, before lithium concentrations are high enough to process economically, which is part of why lower altitude sites in Chile and Argentina developed decades before anyone seriously tried it 4,000 meters up on the Tibetan Plateau. The other half of the breakthrough happened in a lab, not a lake bed. For years, the mineral lepidolite was considered a consolation prize. Lithium researchers knew it was there in huge quantities across Jiangxi, Hunan, and Inner Mongolia. But the old extraction processes were energy hungry and left behind large volumes of waste, which made lepidolite lithium expensive compared to spodumene or brine. The China Geological Survey confirmed that new extraction technology has now made it possible to process this lepidolite at industrial scale, effectively unlocking around 10 million tons of lithium that had been sitting in Chinese ground for decades, chemically present but economically invisible. That's the real story underneath the headline number. It wasn't just that geologists found new rock. It's that engineers found a way to finally use rock that was already known about. The steel and silicon side of this story, nobody saw coming, is what China's battery makers were already doing, while the geologists were still counting tons in Tibet. Two companies dominate this part of the story, CATL and BYD. KTL alone controls roughly 43% of China's domestic EV battery market. And together with BYD's share of around 22%, the two companies account for close to two-thirds of every battery installed in a Chinese electric vehicle. Globally, Chinese manufacturers control more than 70% of EV battery installations worldwide, according to SNE research data. That is an enormous amount of demand sitting on top of a supply chain that, until recently, leaned heavily on imported raw material. BYD took a different approach than most of its competitors. Instead of relying purely on third-party suppliers, it built vertical integration into its own business, controlling everything from lithium mining partnerships in Chile, Africa, and Brazil, down to the battery cells and the finished car. That strategy paid off during the 2021 to 2022 global chip shortage, when BYD's sales surged even as competitors lost production to supply chain chaos. KTL, meanwhile, has been hedging its bets on the chemistry itself. The company has been pushing sodium-ion batteries as a parallel technology, batteries that don't need lithium at all, with its Naxtra sodium-ion line reaching energy densities competitive with some lithium chemistries and mass production beginning in December 2025. Industry analysts now expect sodium-ion batteries to reach cost parity with lithium-ion by the end of 2026. Put those two threads together, and you get a supply chain that is hedging in two directions simultaneously. More domestic lithium coming out of the ground in Tibet and Xinjiang, and a growing sodium-ion alternative that reduces how much lithium the whole system needs in the first place. That's not a company betting on one breakthrough. That's an industry building redundancy into its own supply chain. The same instinct that makes an engineer add a backup generator, even when the primary power grid works fine. The world does not typically wait quietly on the sidelines when a supply chain shifts this significantly, and this case is no exception. China's jump from 6th to 2nd place in global lithium reserves and its emergence as the third largest Salt Lake lithium resource base has been closely watched across the industry precisely because it changes long-term price assumptions for anyone building batteries. Chile, still home to the world's largest lithium reserves, continues to expand its own salt flat production to defend its position as the top exporter. Australia, historically the largest producer of mined spodumene ore, has kept investing in processing capacity, so it isn't left shipping raw rock while other countries capture the higher value refining step. South Korean battery makers, who compete directly with KTL and BYD for global contracts, have been diversifying their own lithium sourcing agreements to avoid overexposure to any single country's supply. And in the United States, new lithium projects, including brine and clay deposits, have moved forward specifically framed around reducing reliance on both South American and Chinese supply chains. Japan's battery and materials firms, long dependent on imported spodumene and refined lithium chemicals, have been expanding long-term offtake agreements with producers outside China to keep their own EV and electronic supply chains diversified. Even within Europe, automakers building out battery gigafactories have cited raw material sourcing, not just cell manufacturing, as the piece of the puzzle they're racing to secure before the rest of the industry locks up the available supply. One lithium industry analyst, speaking generally about the shift in market dynamics, put it simply: new domestic reserves. This large don't just change one country's numbers, they change every other producer's negotiating position. That is the real signal underneath all the individual national announcements. When the resource base for a critical mineral moves, everyone downstream, refiners, battery makers, automakers, has to recalculate. Public reserve announcements are one thing. What actually matters is whether a discovery survives contact with real-world production, and here, the clearest test case is the Jijiaoshan mining area in Linwu County, Hunan Province. In 2025, Chinese authorities confirmed a deposit there of approximately 490 million tons of lithium-bearing ore, classified as an altered granite-type lithium deposit, containing roughly 1.3 million tons of lithium oxide, along with associated rubidium, tungsten, and tin. The work was carried out under China's Mineral Resources Survey Institute, with geological work in the region led by researchers including Xu Yiming, who focuses on critical mineral exploration. By 2026, follow-up assessment work in the same district had refined the estimate to roughly 540 million tons of lithium-bearing rock, reinforcing rather than walking back the original figures. That is what a credible resource discovery looks like. Not a single triumphant announcement, but a number that survives a second round of scrutiny a year later and comes back roughly the same, or larger. Local officials in Chenzhou, the city that administers Linwu County, have framed the deposit as long-term feedstock for the region's cathode and battery manufacturing base, shortening the physical distance between mine and factory. That distance matters more than it sounds like it should. Every kilometer of supply chain between raw ore and finished battery is a kilometer of cost, transport emissions, and geopolitical risk. So how big could this actually get? If China's newly confirmed reserves, roughly 30 million tons of new lithium were identified since 2021, along with the 14 million tons of Salt Lake lithium and the Hunan deposits, convert from resource to active production over the next decade, the country would be positioning itself to supply a meaningful share of its own battery industry from domestic ground for the first time in the EV era. China's lithium-ion battery production alone hit 890 gigawatt hours in the first 10 months of 2024, up 16% year over year. And that number keeps climbing as EV adoption grows in China, Southeast Asia, and increasingly Europe. Every ton of lithium that comes from Xinjiang or Qinghai, instead of a container ship from Australia or Chile, is a ton that doesn't carry the same shipping emissions, currency risk, or exposure to a single foreign supplier's export decisions. Scale that across an entire national battery industry, and you're not just talking about a mining story anymore. You're talking about the raw material foundation for a meaningful share of the world's electric vehicles and grid storage batteries shifting to more diversified and more domestically secured ground. None of this means the story is finished, and it would be dishonest to pretend otherwise. Confirmed resources are not the same as active mines. Turning 14 million tons of Salt Lake lithium sitting under the Tibetan Plateau into usable battery material means building evaporation ponds, processing plants, and transport infrastructure at some of the highest, most remote elevations on Earth, in a region where construction seasons are short and logistics are genuinely difficult. That takes years, not months, and it takes serious capital. The lepidolite breakthrough, too, still needs to scale from confirmed lab and pilot-level extraction technology to full industrial output across multiple provinces, and industry analysts have already noted that these new finds are unlikely to meaningfully shift lithium-ion battery markets in the near term. There's also an environmental dimension that deserves honesty, not a footnote. High-altitude Salt Lake ecosystems on the Tibetan Plateau are fragile, and large-scale brine extraction, even the relatively low-impact kind, changes local water tables and ecosystems in ways that take careful, sustained monitoring to manage responsibly. And there's an access gap worth naming plainly. The infrastructure needed to develop remote, high-altitude, or hard rock lithium deposits favors regions and companies that already have capital and technical expertise, which means the benefits of this shift won't be evenly distributed, even within China itself. The gap here isn't between what's scientifically real and what's exaggerated. It's between what's now technically possible and what will actually get built, financed, and operating at scale over the next 5 to 10 years. That gap is normal for any resource story this size, and it is worth remembering the next time a single headline promises an overnight transformation. Go back to that battery in your pocket for a second. It doesn't look like much. A sealed rectangle of metal and plastic, easy to ignore until it hits 1%. But underneath that unglamorous object sits one of the most consequential resource questions of the next decade, one that stretches from evaporation ponds 4,000 meters up on the Tibetan Plateau to a phone charging on your nightstand tonight. The world didn't run out of lithium. It just spent decades looking in the same three places, while a fourth one was sitting there the whole time. waiting for the chemistry and the mapping to catch up. If you found this one interesting, there's a lot more where it came from, so hit subscribe and turn on notifications so you don't miss the next breakthrough. Here's a real question worth sitting with. If a resource this large was technically present in Chinese ground for years before anyone could economically extract it, what other known but unusable resources do you think are sitting under our feet right now, just waiting for the right piece of chemistry to unlock them?